members and guests from near and far. Welcome to Siena Heights University's Environmental Speaker Series, sponsored by the William Issa Endowment. I'm Tom Wasmer, Assistant Professor of Biology and Chair of the Sustainability Committee here at Siena Heights University. Before we hear from Mark Jacobson, how we can get rid of all fossil and nuclear fuels in 30 years or even less, and reduce the inevitable consequences of global climate change to a minimum. I want to thank the members of the Sustainability Committee for all their work in bringing this event together, and also to prepare the various tasks involved with this event. The Sustainable College Committee of Siena Heights University was founded only about a year ago and strives to increase the coverage of sustainability in all syllabi that we teach and all curricula that we use, and to promote sustainable operations throughout the campus and all our operations. We are therefore in need of your donations to allow us to join ASHE, the Association for the Advancement of Sustainability in Higher Education, and use their reporting and benchmarking tools to create a baseline for Siena Heights University to allow us to compare our school to other schools, comparable schools in higher educations, and to monitor our year-to-year progress in sustainability. A donation form is conveniently included in your program. So please help us move towards more sustainability here at Siena Heights. And now please lend me your hands to welcome Sister Sharon Weber, Vice President of Academic Affairs of Siena Heights University, who will officially open this event.
It is a privilege to welcome all of you to this evening's presentation. On behalf of Sister Peg, our President, who is unable to be with us this evening, and on behalf of the whole university community. We are especially grateful to welcome Dr. Mark Jacobson into our midst to challenge us to consider how we might help increase our ability to provide the energy we need through the use of renewable energy sources. The Solutions Project, which he co-founded, combines science, business, and culture to design and implement clean energy plans for states and countries. It is his respect for an approach of partnerships that makes it so important that all of us are here tonight, so that each of us can see how we can help preserve the earth, so we can enjoy that down to the 7th generation and beyond. We're also grateful for the funding that has made the evening possible from an endowment honoring William Issa, a young man who used his too few years to demonstrate a commitment to the quality of our environment. And we want to thank Tom Wasmer and the members of the Sustainability Committee who did the work to pull this together, as well as all members of the Siena community who helped over the years to make us a more sustainable environment, even to, turning off your computers, things like that. So then let us begin our reflections and listening with a prayer. Good and gracious God, we come together this evening with hearts full of gratitude for the gift of the earth, its beauty and its generosity to those who inhabit it. We come in celebration of the promise of new life which surrounds us in the early days of spring, in the return of daffodils and birds and robins and green buds. We ask you to bless Dr. Jacobson, his words to us, and his work on behalf of our world. We ask you to bless us with eager minds, listening ears, and ready hearts, that we recognize our place in the world and help to make the spring times as wonderful for future generations as it is for us. We ask these blessings in the name of our brother Jesus, whose stories of seeds and sheep and birds of the air told of his closeness to and love of the earth. And so we say, Amen. Amen.
Hello, my name is Dr. Jun Suji, and it is my pleasure to introduce to you our featured speaker. Dr. Mark Jacobson is a professor of civil and environmental engineering at Stanford University. There, he is also the director and co-founder of the Atmospheric Energy Program. Dr. Jacobson is also a senior fellow at the Woods Institute for the Environment, as well as at the Precourt Institute for Energy. He has earned many distinctions, including the American Meteorological Society Award, an American Geophysical Union Ascent Award, and the Global Green Policy Design Award. This evening, Dr. Jacobson will share how the problems of global warming, air pollution, and energy insecurity can be addressed through the Solutions Project by converting our energy infrastructures to renewable sources such as wind, water, and solar power. Please join me in extending a warm welcome to Dr. Mark Jacobson.
Thank you all for those really kind introductions and for inviting me to come to this great place to give a talk, to talk about how we can change to a clean and renewable energy future. So I want to discuss energy plans that we've been developing and apply them also to Michigan. But first I want to talk about the problem a little bit before we get into the solutions. From our point of view, why do we care about solving these problems? Because there is a lot of energy available worldwide and in the United States, so we could go on for decades to centuries without worrying about clean energy if we weren't concerned about air pollution, climate, and energy security and price security. So from an air pollution health point of view, this is my main interest. 4 to 7 million people die prematurely each year from air pollution, primarily from fossil fuels and solid biofuels. Most of these are developing countries, and about 20% are children under the age of 5 years old. And in the United States, there are about 63,000 premature deaths each year. These are from cardiovascular disease, respiratory illness, complications from asthma. And these are avoidable deaths, and they're due to primarily particulate matter in the air, but also from gases like ozone that form from chemicals emitted through combustion technologies. And this cost the U.S., just those 63,000, based on the statistical cost of life, cost the United States about 3% of its GDP, or over $500 billion per year today. Global warming is a growing and rising problem, and U.S. emissions alone are expected to cost the world over $3 trillion by 2050 per year. And these are due to the rising sea levels, to agricultural losses, to droughts, to severe weather, and other impacts. Just to give an example, if all the ice melts worldwide, that would raise sea levels about 70 meters, and that would flood 7% of all the world's land. And most people live along the coast where the flooding would occur. So these costs will be enormous in terms of protecting the coastlines and to remediate damage that is being caused. So the other issue is price security. With conventional fuels, you have limited resources, although some of them are, we don't know exactly what those resources are, but they are limited, and someday they will run out. Prices gradually rise over time. They'll turn out with clean and renewable energies, such as wind and solar, for example. They have zero fuel costs. So even though they have higher capital costs, you stabilize the price of energy, so you hedge against rising prices over time. And so if prices rise over time, you could lead to social, political instabilities. And we want to avoid those problems. So these are all drastic problems that require immediate and drastic solutions. And just a little bit more about the problems, just to give you an idea of air pollution. This is what Beijing, China looks like a lot of the time. This is one particular set of days in 2013, but it looks like there's a lot. It's equivalent to smoking 2 or 3 packs of cigarettes per day, living there in many megacities of the world. And if you think that's rare or uncommon, well, in the United States, Los Angeles was like that in the 1970s and 60s and 50s and 40s and 30s, actually back to the early 1900s. And these are the lungs of a teenage non-smoker who died in a car crash in Los Angeles, and it was equivalent to smoking 2 packs of cigarettes per day. The average American who lives in a big city loses about 6 to 8 months of their life due to air pollution still. And although there are 63,000 deaths I mentioned, but there are hundreds of thousands of people who suffer from asthma, cardiovascular disease, respiratory illness that are also triggered by noxious air pollution. From a climate point of view, the Earth is warming primarily in the northern hemisphere, and if you go further north to the Arctic, you get even more significant warming. This is a map showing the changes in temperature worldwide since 1900. And you can see the brunt of the warming is near the Arctic, where it's most sensitive to changes. And the temperature change has been about 0.9 degrees Kelvin or Celsius, which is on the order of close to 1.5 degrees Fahrenheit on average worldwide. But you can see in the Arctic it's up to 4 degrees Celsius or even higher. And that's causing a melting of the Arctic ice. The Arctic sea ice may disappear entirely within 10 to 30 years. And the ice reflects light because it has a reflectivity of about 65%, whereas the ocean below has a reflectivity of only about 8%. So if you melt the ice, then you absorb more sunlight, heating the ocean even faster, and that triggers positive feedbacks that cause more warming worldwide. In particular, it also causes severe storms because hurricanes, their intensity is driven by high sea surface temperatures. Now, this warming, so these are 2 major problems, but I want to point out just one more problem associated with warming that really ties everything together and then really gives motivation for the solutions. Although most of you can't see this because the screen's probably too small, but I'll just point out what this is. On the right, it's a chart showing, on the right, the net temperature change on the Earth, which is pretty much close to the last number I showed from that 0.9 degrees Kelvin, although this is 0.8 degrees Kelvin. And that's the net warming that has occurred. But greenhouse gases are actually causing over 2 degrees warming. And soot particles, black carbon, which comes from diesel exhaust, jet fuel, kerosene burning, biofuel burning, biomass burning, this black smoke, and also brown carbon, which is brown smoke that comes from combustion. That's the second leading cause of global warming after carbon dioxide. Methane is the third. And soot, which primarily from fossil fuel and biofuel sources, it also contributes to warming. And those are particles that also affect people's health. So of those 4 to 7 million deaths per year, 90% are due to particles in the air. And some of those are soot particles, which cause warming, but most of them are actually what we call cooling particles, which are reflective, containing lots of oxides of sulfur, for example, ammonia, some nitrate species. We don't want to bore you with all the chemicals, but cooling particles are part of pollution as well, and they mask half of global warming. So if we clean up all the air pollution worldwide, and we can do that because the pollutant sources, they come right out of tailpipes, so you can put particle traps, you can put sometimes more efficient fuels. You can't clean everything up, but you can clean up a lot of particles. It's hard to clean the gases up because they pass through a lot of the filters. But if you clean up the particles, you actually clean up both the warming particles and the cooling particles, and you suddenly double the amount of global warming that's occurring. So air pollution is hiding half of global warming that's in the system. And we want to clean those particles up because they cause all these mortalities. So there are 2 ways you can solve the total problem. You can focus on the soot particles, control the black carbon, like put more diesel traps on buses and trucks and construction machines, and reduce biomass burning, and stop gas flaring, because natural gas flaring is a source of black carbon. Now would reduce some warming and help health problems, but that doesn't address the greenhouse gases, and it doesn't address the rest of the air pollution problems, and it doesn't actually solve the global warming problem. Or you can eliminate all the particles and the gases together. And there's only one way to do that, and that's to change the energy infrastructure of states and countries in the world. So we want to eliminate everything to the left. And there's one little piece there, the urban heat island effect, we're not going to be able to eliminate, and that's the heating of cities due to the addition of construction materials to surfaces that prevent evaporation. Evaporation is a cooling process, so if you prevent evaporation, you warm the surface, and that's what happens with the urban heat island effect. But that's a relatively smaller component on the global average. So we want to change the energy infrastructure, so that's what I want to talk about today. So this is how we propose to do it. I know you can't read it, it's all described what I've got here. But we have to look at all purposes. So all purposes is electricity, transportation, heating and cooling, and industry. And the idea will be to electrify everything that we can and use clean electricity to provide that electricity. And some of the electricity will be used to produce hydrogen that will be used for some applications. Now for electricity, what we call the clean electricity generators will include wind, solar photovoltaics, which are rooftop solar or to go in power plants, or what we call CSP, concentrated solar power, which is where you focus light off of mirrors to a central tower receiver. So this tower receiver gets a lot of light focused on it, and you heat a fluid, the fluid goes to really high temperature. That fluid can be stored overnight and be used at any time, either day or night, to be run past water to heat the water to create steam, to run a steam turbine to generate electricity. So CSP is a way that you can not only generate electricity from sunlight, but also store energy to use it for electricity at some other time of the day. Geothermal power, in this sense, we're talking about two boreholes where water goes down one, you hit hot rocks, the rocks heat up the water comes up the other hole, you have hot water, the steam from that runs a steam turbine to generate electricity, and the water gets recycled back into the hole, so you can prevent it from escaping to the air. Hydroelectric power, we use existing hydroelectric, and this is a way to store energy because hydro is a storage that you can turn on and off within seconds to provide electricity when you need it. And then a tiny amount of tidal wave power. Then these electricity options, for transportation, we'd use these to power battery electric vehicles and hydrogen for some hydrogen fuel cell vehicles. The hydrogen fuel cell will be mostly for heavy duty, like ships. We do some cryogenic hydrogen, which is hydrogen at low temperature, high pressure for aircraft, such as the space shuttle use cryogenic hydrogen. And for some long distance trucking where you'd use hydrogen combined with electricity. Because battery electric vehicles, it turns out, are just much more efficient than hydrogen fuel cell vehicles, even when the hydrogen is produced from electricity, about 3 times, but they're both very clean. It's just that battery electrics are more efficient, so we want to use those as much as possible. For heating and cooling, we use heat pumps. These are all, by the way, these are existing technologies. Heat pumps, which extract heat out of either the air or the water or the ground to heat the air or to heat water. And some electric resistance heating, but again, heat pumps are more efficient than resistance heating, and some solar hot water preheating. For industry, we'd electrify everything and use some hydrogen as well, through all these different technologies. Now, that's for producing the energy for these different technologies. It turns out because the wind doesn't always blow, the sun doesn't always shine, we need some kinds of storage. And I've mentioned 2 kinds of storage, CSP, concentrated solar power, and also hydroelectric. But there are others as well that we use also, and they include pumped hydro, where you have 2 reservoirs, or it could be a lake and a reservoir where when you have extra electricity, you use that electricity to pump water up a hill, and then when you need that electricity, you can let the water drain down the hill back to the original reservoir and run through a turbine to generate electricity, just like a hydroelectric dam. And this way, the water gets recycled up and down, and this is a way to really move the time of your electricity use. And then for heating and cooling, we'd use existing technologies that are inexpensive. One's called sensible heat, where you just have a tank of water basically, and when you have extra electricity, you heat that water, and you store hot water. And then when you need heat either for air or water, you can then take it out of that hot water. Similarly, ice storage, it's very common. It's where you have extra electricity, you can produce ice, for example, at night, store it under a building like our university, since 1998, has had a big ice cube under a building. And you use that for chilled water during the day. And soil storage. Soil storage is, you can use this seasonally. So there's a community in Canada called Drake Landing, where for 8 years, the whole community is run on seasonal heat storage, where in the summer they have solar collectors on their roofs. They heat a glycol solution. The solution goes to heat water. The water goes down into the soil in these boreholes, and the soil heats up to 80 to 90 degrees Celsius, and it's insulated. And then it stays there till winter, and then wintertime everything's run in reverse, and it heats 90% of their buildings. So that's called, and that costs, just to give an idea of the cost, the batteries cost about, just to put it in perspective, $600 per kilowatt hour of stored energy, whereas soil storage is less than $1 per kilowatt hour. Ice storage is around $35, $38. CSP, concentrated solar power with phase change materials, about $15 to $18 per kilowatt hour. So batteries, if they come down in price, they're great, but right now they're very expensive, except they have reached some price parity in vehicles that prefer electric vehicles. Now, finally, we've used hydrogen, as I mentioned, for transportation and industry, and that's a form of storage as well. And we use a technique called demand response, which is where utilities will basically give incentives to companies or individuals not to use power at certain times of the day, to shift their time and peak demand. So I'll show you some results later on where we actually simulate the entire United States, combining wind, water, solar solution with the storage to actually try to match the load on the grid for a 6-year period. So I'll show you that a little bit later. But okay, so I want to talk briefly about why some technologies we're not considering, because you all ask questions, well, why should we use natural gas, etc. And I don't mean this to be critical of other technologies, although it'll come across that way. But I'm really saying that it's not that these aren't, in some respects, some of these are not better than what we have today. It's just that they're not going to be quite so good, sometimes not even close to being so good, as the wind, water, solar technologies. These are critical problems that we have to solve immediately. So every dollar you spend on a solution that's not quite so good, or not nearly so good, that's one less dollar that you're going to spend on solving the problem. And some of these solutions, they'll solve part of one issue but not the other. So take natural gas. Natural gas, even though the CO2 emissions, carbon dioxide emissions per unit energy are about half those of coal, the CO2 emissions are still about 50 to 70 times higher per kilowatt hour generated than wind power. And there's also a lot of methane emitted from natural gas that exceeds that of coal significantly. And over a 20-year time period, methane has what's called a global warming potential, or potential to warm the planet, about 100 times more than carbon dioxide. That's over a 100-year time period. Over a 20-year time period. Over a 100-year time period, it's on the order of 30. But that's not the only issue. Black carbon from natural gas flaring in particular is a danger for the Arctic sea ice. And coal, ironically, which causes more air pollution health problems than natural gas, ironically, some of those pollutants include these cooling particles that mask a lot of the global warming. So if you actually account for the higher methane and black carbon from natural gas and the lesser cooling particles, you actually find that especially over a 20-year time period, that natural gas causes more warming than coal, but less air pollution. But they're both really bad, so I'm not trying to say that one is good, one's bad. They're both very bad compared to what we could have. Now, in terms of air pollution, natural gas still, of the 63,000 deaths per year in the US, about 5,000 are due to natural gas mining, transport, and use. Now, coal has about 15,000 deaths. And hydrofracking, which is drilling through shale rock, cracking rock using water laced with chemicals under high pressure, not only devastates the countryside. You can see there's an image here of lots of natural gas wells. And there are over 1 million natural gas wells in the United States alone that have been drilled. And to put in comparison, if we want to power 50% of all the United States with wind, we need only 500,000 more wind turbines. So half the number of these holes. And those holes, in the case of wind, are only 5 meters wide. I'll get to that later. Now, hydrofracking increases methane leaks as well. So why not what we call clean coal or coal with carbon capture? That's where you take the exhaust from the coal-fired power plant and you pump it underground, try to store it. That actually reduces about 85 to 90% of the CO2 emissions that come out of the stack. However, it does not reduce any of the emissions from the mining or transport of the coal. In fact, those go up 25% because you need 25% more coal to run the carbon capture equipment. And you also don't reduce any of the other pollutants from coal, because the carbon capture equipment does not reduce sulfur oxides, mercury, hydrocarbons, carbon monoxide, particulate matter. So you actually increase all the other pollutants 25%. So it really should be called dirty coal because it's actually dirtier in terms of air pollution than normal coal. But it does reduce CO2 overall compared to coal without carbon capture. But it's still, even with all that carbon capture equipment, you still have 50 times more CO2 per kilowatt hour than wind power. So we don't think that's a solution, but nevertheless, it's not even being applied on any commercial scale. Okay, why not nuclear? Okay, so nuclear is one that it certainly has advantages over a lot of the current fuels. And in our case, we don't think that it's quite so good as the other technologies. And there are a few reasons. One is that the air pollution, you still have air pollution if you're running the regular electric power grid to refine and mine uranium. So that's a very energy-intensive process, the mining and refining of uranium. In fact, in the United States, there are 2 coal-fired power plants whose sole purpose is to refine uranium for both nuclear energy and weapons. So that's about half the emissions from nuclear or from the regular grid refining uranium, also the construction of the plant. But it also takes so long to plan, permit, and construct the nuclear power plants. In the United States, the average is 10 to 19 years. And whereas 2 to 5 years for most wind and solar farms. So after that 5 years of putting up a wind or solar farm, if you had instead opted for nuclear, you would be waiting another 5 to 14 years running the regular electric power grid. So there are emissions associated with that. So that's how you get 9 to 25 times more CO2 emissions per kilowatt hour, and also air pollution, from nuclear than wind power. There's also risks associated with it that you don't have the same risks with wind, water, and solar, such as risk of nuclear meltdowns in reactors. 1 and 1.5% of all nuclear reactors ever built, there have been 440 to date, have melted down to some degree. And weapons proliferation. Believe it or not, 5 countries in the world have developed nuclear weapons secretly under the guise of civilian nuclear energy programs. And this is a risk. Doesn't mean it's going to happen, but if we want to power the world with nuclear, we need about 16,850 megawatt nuclear plants. Right now we have 400, well, they're actually only less than 400 in operation because about 40 plus were retired in Japan and Germany and also some other European countries. And so even if we powered 5% of the world with nuclear, we'd have to double the number of plants to 800. And this means more countries of the world would participate in this, and some of them may be interested in developing weapons from that. So it's a risk that you don't have to deal with the wind, water, solar technology. And then finally, there's unresolved waste issues. So what about biofuels? So I'm going to give an example. Well, biofuels, liquid biofuels like ethanol in particular, whether it comes from corn or cellulosic material or sugar cane, or if it's biodiesel, you still have to burn it right now, for the most part. And there are some technologies where you can run it through a fuel cell, but it's primarily burned. And when you burn it, you still produce air pollution. In fact, you have different air pollutants, mostly aldehydes from alcohol fuels, as opposed to aromatics from gasoline-type fuels. And aldehydes actually are a little more potent at forming ozone. So you'll increase the ozone production in the United States, and that's one of the causes of mortality. So there's actually no benefit in terms of health, of using an alcohol fuel for transportation. And there's marginal climate benefits. It depends really on what type of fuel and how it's produced. For corn ethanol, most people think it's a wash between gasoline and corn ethanol in terms of the carbon. Cellulosic ethanol, people think, well, there might be a benefit, but it depends on the cellulosic ethanol in terms of carbon. But at best, in all possible best worlds, it might be 50%. And that sounds good, but with a battery electric vehicle powered by wind, you reduce 99.8% of your emissions. And plus, those 50% estimates ignore land use change. When you start growing switchgrass, say for cellulosic material for ethanol production, then the price of land changes, and that triggers deforestation in other parts of the world. And that changes the carbon balance. And so some studies have found that you actually increase the total carbon emitted worldwide when you have large-scale ethanol. But regardless, cellulosic ethanol doesn't exist at the commercial scale. So all we're left with is corn ethanol, which there's no benefit in terms of carbon and air pollution. But let's just look at the land part. So this is how, to run the United States vehicle fleet on cellulosic ethanol, it would take on the order of 20% of the entire United States to grow switchgrass, including Alaska. So that represents this size dot. For corn ethanol, it's about 14%, and that's this size dot. So this will never happen. I mean, we are never going to commit this much land, especially when, photosynthesis is 1% efficient. So only 1% of the energy from the sun hitting the ground goes to produce energy for a biofuel. Whereas you put a solar panel in the same place, solar panels are 20% efficient. So you get 20 times more energy over the same land. Or conversely, you need 1/20th the land to produce the same energy if you use solar photovoltaics versus a biocrop. Now, nuclear power actually doesn't take up a huge amount of land to power the US vehicle fleet. It's about the size of Rhode Island. So, put nuclear for Rhode Island to power the vehicle fleet. Now, wind, it has two types of areas that we can talk about. One is the spacing area, which is represented by the black dot, which is about 0.5% of the United States. So it's around 1/30th the land area for corn ethanol. But the red in the middle, which you might not be able to see, is the footprint on the ground. Because wind turbines are poles on the ground, surrounded by a little bit of concrete base. And you need separation between them to prevent interference of one turbine's energy with the others. So that's the black spacing. But that spacing can be used for multiple purposes: rangeland, farmland, open space, or it could be offshore as well. But the footprint on the ground for wind to power the entire US vehicle fleet is less than 3 square kilometers. As a result, the cost of driving an electric car is much less than a gasoline. For example, if the average price of gasoline were $4, I'm not sure what it's here, but around where I live, it's around $4 a gallon. If you drive a electric car, it costs 80 cents a gallon equivalent versus $4 for gasoline. So if you drive for 15 years, 15,000 miles per year, you'll save $20,000 in fuel costs. So that electric car has to be $20,000 more expensive for it not to be worth getting an electric car. Not to mention all the other benefits of the electric car: accelerates better, fewer breakdowns, fuel it in your home, and it's actually some of these newer cars are rated as the the most safest cars in the world because of the more crush space in the front and better materials that are being used, but a lot of other cars can do that. But the crush space is actually important because your normal car, you have a big engine. Electric cars, there's nothing in the front, it's a trunk. You have a trunk in the front and the back. So anyway, so electric cars are one example of how you reduce your energy demand by switching to electricity for everything. And in the United States, there would be a 36% reduction in power demand by grid conversion because there's a higher fraction of transportation in the US than the world on average. And transportation is where you get the best benefit in terms of electrification. In Michigan, it's also about a 36% reduction in power demand. So what we want to do, and I'm going to talk for the next few minutes about, well, can we power then, these are 2050 numbers, can we power the United States and Michigan 100% with wind, water, solar? So to do that, we would have to satisfy 1.7 terawatts of power demand in the United States and 0.042 terawatts, or in other words, 42 gigawatts of total power demand. This is end-use power demand for all purposes in Michigan. So here's one way to do it in the US, and this was we developed plans for each of the 50 United States, looking at the resources available and looking at land areas, rooftop areas, a lot of other factors. And we developed plans for each of the 50 states, and this is the sum. It shows kind of the combination of everything. So in these plans, and this is not a unique plan, there are other possible combinations. And in this set of plans, it would be 31% onshore wind, 19% offshore wind, so wind would be about 50% of the total. About 4% rooftop photovoltaics, 3.2% commercial government rooftop photovoltaics, about 31% utility scale solar PV, about 7.3% concentrated solar power, 1.2% geothermal, 2.8% hydroelectric, and this is almost all existing hydroelectric, and about 0.5% of wind plus tidal power. This would power the entire US for all purposes. So in terms of wind, it's about 500,000 total wind turbines. Rooftop PV systems on residences, that 4% is about 80 million 5 kilowatt systems. In any case, I'm not going to bore you with all these numbers, but what I will show you is this map. This is the land areas required to do this, to power the whole US in 2050, accounting for economic growth and all end uses, eliminating global warming, eliminating air pollution, providing stabilizing energy prices. For the wind, as I mentioned, 31% onshore wind. That would take, the spacing area is about 1.7% of the US, and all that land can be used for multiple purposes. The red dot in the middle is 4.5 square kilometers of actual physical land on the ground. Offshore wind is another 19%. The PV plus CSP power plants, we assume this takes up new land, so it's about 0.35% of the US, powering 38% of all power. Geothermal is 1.2%. Rooftop PV is a total of 7.2%. That's going on existing roofs. So the overall, to summarize the land area required, for the footprint, it's less than 0.5% of the US. For the spacing, it's another 1.7% of the US for land, on the land. And that can be used, again, for multiple purposes. Okay, so what about resource availability? Is there enough wind in the world and solar to do this? And in the United States? Well, there's actually better resources of both solar and wind in the United States than on the world average. This is a solar map of the world. And I just want to, well, in the United States, solar is good in every state, but it's better in Southwest states. But the total world resource of solar is about 340 terawatts over land and high solar locations. And what we need in 2050 for the world is about 15 terawatts. So there are about 23 times more, there's about 23 times more solar available worldwide in high solar locations over land than you need to power the world for all purposes. So in wind, there's about 5 times more wind in high wind locations worldwide than you need to power 15 terawatts of the whole world in 2050 for all purposes. So there's more wind, solar than wind, but there's enough wind as well. In the United States, the wind, primarily in the Great Plains, and off the coast. The East Coast is the greatest untapped source of resources. The Great Lakes also have great resources, and as you know, Michigan, you have really good resources. So speaking of, well, I'll come back to Michigan in a second, but I want to talk first about stabilizing the grid in the United States. So if you have all these intermittent resources of wind and solar, 500,000 wind turbines, you know, they're not only intermittent, the wind doesn't always blow, the sun doesn't always shine, but they also compete for the same energy. You know, the wind has a finite amount of energy in it, and if you put up one turbine, you can extract the maximum amount of energy by that turbine. But if you put up two turbines next to each other, they're competing for the same wind, so each turbine is going to get a little less than they would if there were no other competing turbines. So we're trying to see if we can match power demand on the grid in 2050 with our 50 state plans. So the first step was to develop time-dependent wind and solar resource maps and quantify winds every 30 seconds and solar every 30 seconds. And so to do that, we put into a model that accounts for extraction of energy by the wind turbines, all 500,000 turbines in the US, state by state, and determine what that competition, how much energy that would cause a loss of. How much would you lose? How much energy would you lose by competing wind turbines against each other? It turns out with 500,000 turbines, you lose about 8.5% of the energy, compared to if each turbine was operating as if there was no competition. So that has to be accounted for. That's a loss to the wind turbines, in addition to transmission distribution losses. But we did that, and we still developed time-dependent wind resources, and also did the same thing for solar, accounting for cloudiness and different angles of the sun, in the model, climate model. And then we compared that, we had all the other wind, water, solar resources. We had the estimated 2050 loads every hour based on current loads and projected future loads. And accounting for this extreme variability in wind and solar, and then combining that with storage, we developed a grid, what's called a grid integration model to match power demand with supply. And here's the result. This shows for a 6-year period on the top, shows month-by-month averages. The red line, well, it's hard to see, the red line is the total supply of energy each month for 6 years. And the blue dots are the total demand for energy plus changes in storage. And we were able to match them exactly every month, but not only every month, every hour for 6 years, and not only every hour, every 30 seconds for 6 years, with no loss of load. The industry standard for loss of load is 1 day in 10 years. And we ran it, well, we only ran 6 years, but we had 0 loss of load in 6 years over the entire US with 100% wind, water, solar system. The bottom shows a 4-day period each hour, showing the same thing, the total demand, the total supply in red and the blue dots are the demand. And even though I absolutely can't see these graphs, you know, this is another 4 days, and the top is the sum of the red line is the every hour for 4 days of wind and solar plus geothermal, hydro, etc. resource. The blue is the load. Below that shows the breakdown of the solar and the wind, and all the next one shows the breakdown of all the supplies, and the bottom one shows the breakdown of the demands, plus the changes of storage and the losses, transmission, distribution losses, storage losses. Anyway, the point is, the bottom line is, it is possible to power the whole US with these technologies with 0 loss of load. In fact, yesterday there was a news story from one of the leaders of the California. In California, there's a group that looks at utilities to balance, and this leader said that it's also possible in California to go to 100% renewable energy. And this was a utility person saying that. Says because California's been pushing the limit in terms of how far they can go, and they see no reason they can't go to 100% renewable energy. Okay, so what about Michigan? So these are the most recent numbers, and those of you who've seen the Solutions Project website where you can click on a map, in fact I think there's one in the brochure, these numbers are updates compared with those numbers. So these are the most recent numbers, and you know, we've been working on this non-stop for the last several months to really refine this. But this is not the only possible solution. There are other possibilities, it's just that this is one possible solution. How do you power Michigan for all purposes in 2050 with wind, water, solar? Well, one scenario is 40% onshore wind, 30% offshore wind, 3.5% rooftop PV, 3.2% commercial government rooftop PV, almost 19% solar PV power plants, 2% concentrated solar power, no geothermal, 0.7% hydro, which is mostly, it's all existing hydro, no tidal, and about 1% wave power. That's one scenario for powering Michigan for all purposes. Now, we've done this also for now 139 countries of the world, and this is for China. Can we actually power China for all purposes? And in this case, it would be 16% onshore wind, 18% offshore wind, 7% rooftop PV on residences, 7% commercial government rooftop PV, 34% solar PV power plants, 10% concentrated solar power plants, 0.6% geothermal, 6.8% hydro, 0.03% tidal, and 0.25% wave power. Okay, so what about, people ask, well, okay, if you put all these offshore wind turbines off the east coast of the United States, for example, won't they be destroyed by a hurricane? And Walmart is very happy to know that if you actually put a lot of wind turbines offshore, not only can they generate power for their stores, but they can also save their stores from being destroyed. And I'll tell you why I mentioned Walmart in a second. So this is we ran numerical simulations with a climate model the same climate model actually that I showed you before, that extracts kinetic energy from the wind with wind turbines. And we simulated Hurricane Katrina. And we were able to simulate the actual peak wind speeds and minimum pressures and track of the hurricane pretty exactly without the turbines. And then we put in tens of thousands of wind turbines to the southeast of New Orleans and ran the same hurricane through. And this shows wind speeds. On the left is no turbines, on the right is a wind farm to the southeast of New Orleans. And you can see the wind speeds are reduced where the turbines are. And what the turbines do is they take out, extract energy from the wind. That slows down the winds locally. That reduces wave heights. Waves are critical for moving instead if you don't have waves, winds would just go in a circle around a hurricane. But waves create friction that cause the winds to migrate towards the center, converge towards the center, where they spiral around the eye wall upwards. And then they get drawn out by faster winds aloft. They're drawn out faster at the top than they come in at the bottom. So that reduces the pressure, drops the pressure in the hurricane, which increases the pressure difference between the inside and the outside, which speeds the winds normally and increases wave height. So there's a positive feedback normally by creating waves. Hurricanes would not occur without waves. But what you do when you have a lot of wind turbines is you reduce the wave heights, you reduce the friction, you reduce the convergence, you increase the central pressure. So what this is doing, while it's reducing the outside winds of the hurricane, it's actually increasing the central pressure of the hurricane too, dissipating it from the inside, such that by the time the center gets to New Orleans or to the turbines, the hurricane is almost dissipated. So you can actually reduce about up to 80% of the storm surge and 60% of the wind speed, peak wind speeds, with large arrays. But you do need a lot of those. I don't want to underplay it. So you have this effect, you need tens of thousands. But these turbines would generate power year-round, pay for themselves. The alternative is putting up seawalls. Seawalls do not pay for themselves. They're basically like for New York City, it'd be like $30 billion to protect a certain portion of the shore. And they only reduce storm surge, not the wind speeds. And so you can put up wind turbines. Now for our plans for the US, we would need a total of 180,000 wind turbines. And a lot of these would be off the East Coast. And the East Coast, the wind speeds, the hurricanes never get past Category 3. And so you really never get to the destruction wind speed of a wind turbine, which is 50 meters per second, which is close to Category 3. So your turbines are safe even if you have a few turbines on the East Coast. So the Gulf Coast, you do get 4 and 5 hurricanes, and that can destroy turbines unless you have a lot. Once you have a lot, you never get to the destruction wind speed of the hurricane. Anyway, this is a little bit of a side, but I do want to say that that's a collateral benefit. But you would not put up wind turbines offshore just to stop a hurricane. I mean, you put them up to generate electricity year-round, and it just so happens that would be an additional benefit. But the reason Walmart liked this was because they lose a lot of storage to hurricanes from severe weather along the Gulf Coast and East Coast. And they also want to go to 100% renewable energy in their storage. So this was a kill two birds with one stone. And so a lot of companies, but to solve this problem, it'll turn out we need to engage companies. And companies do have their own self-interest at heart, but they also are interested in maintaining low-cost energy and stabilizing their price of energy. So there is a benefit of working with the companies to try to solve these problems. What about the cost of energy? People say, well, wind and solar are really expensive. Well, they used to be, but actually wind right now, onshore wind, is the cheapest form of electricity in the United States today, by far, by a factor of 2. And that's mostly for Great Plains wind. The unsubsidized cost of wind in the Great Plains, which is mostly the U.S. average, 3.7 cents per kilowatt hour. These are new. You can run an old coal-fired power plant at 2 cents a kilowatt hour that was grandfathered in and built in the 1950s and doesn't have to meet Clean Air Act regulations. We're talking about new plants and devices. Onshore wind is 3.7. Natural gas, conventional natural gas, combined cycle, 6.1 to 8.7. This is from detailed analyses by Lazard, which is a group that does these cost analyses. So wind is half the cost of natural gas right now. Now, utility scale solar is 7.2 to 8.6 cents a kilowatt hour, so it's in the same range as natural gas as well. I should point out that gas for peaking power to provide energy when you have a really spike in electricity demand is about 18 to 23 cents a kilowatt hour. So gas, when you actually average over all the sources of the gas use, it's not as cheap as just the combined cycle. Now, hydroelectric is about 4 to 6 cents a kilowatt hour, and geothermal is about 9 to 14. Now, what's expensive still is offshore wind is still really expensive, comparatively. And rooftop PV, especially residential, is on the order of 3 times higher than utility scale PV, so that's more expensive. But still, even if this cost a residential rooftop, it will still pay itself off after 8 to 10 years. So if you buy a residential rooftop system, and they're well, at least in California, I'm not sure about Michigan, but they're warranted for 25 to 30 years. Their state requires a warranty that these solar panels be warranted for that long. So you put them on, either you buy them up front, and they'll pay themselves off after 8 years, and then your electricity is free until either the warranty runs out or you die after that. But most of the solar today is done by leasing, so people don't even have to put up upfront money. They have companies that will actually lease solar to you and put it on your roof and take care of everything, so you don't have to worry about it. What about the additional health and climate cost savings? So those are the direct costs, but then on top of that, the climate cost the health cost savings of the 63,000 air pollution deaths per year, it's on the order of $500 billion per year in the United States. And the climate cost savings is another, as I mentioned, $3 trillion by 2050 from US emissions alone. That's global costs. So these additional costs translate to over 6 cents per kilowatt hour for fossil fuels. And so if we look at a wind, water, solar system, and by the way, when we did that grid integration study, we costed out all the storage and the transmission and the generators, and the total cost of energy, including distribution and transmission and distribution, was 11.5 cents a kilowatt hour direct. And that was 2050 cost brought back to 2013 dollars, 11.5 cents a kilowatt hour for the whole system. And that was similar to the fossil fuel system. But the fossil fuel system on top of that has another 6 cents per kilowatt hour of health and climate costs. So it's really on the order of 17 to 18 cents per kilowatt hour. So the wind, water, solar system is going to be less expensive. But just to give you an idea of how wind, water, solar stabilizes prices, if you look at the electricity price in the states with the highest fraction of electricity from wind, the top wind states right now in terms of the fraction of electricity are Iowa and South Dakota, which have 30% of their electricity from wind. The top 10 states, the price of electricity in those states over the last 5 years stayed steady. It actually declined about 0.1% on average. All the other states, their price of electricity went up 8%. Hawaii, the price of electricity has basically doubled from 17 to 34 cents per kilowatt hour in the last 10 years, because you have to transport all this fuel. I mean, take American Samoa, the cost of, you need diesel generators, the diesel fuel that has to be transported, it ends up costing 50 to 55 cents per kilowatt hour, compared to the average in the US for 13 cents per kilowatt hour. So certainly in places that are remote, having some local energy, or even transmitted energy, is ideal. Now, what about jobs? So the National Renewable Energy Lab has models that calculate job production for different energy sources. And from our wind, water, solar generators, we calculate 4.5 million 40-year construction jobs and 2.2 million 40-year operation jobs in the US. So it's about 6.7 million jobs. This would exceed the 3.9 million jobs lost by the fossil fuel and nuclear industries if they were replaced. And finally, if I look at a timeline for transition, the idea is to convert everything by 2050, but by 2030 have 80% conversion. So this means by 2020 that all new generators in electricity, transportation, heating, cooling, and industry should be wind, water, solar. If we don't do this, the top of this graph shows the business as usual, that energy demand will increase. The second line is if we just convert everything, then we're going to have, the light gray is the reduction of energy demand due to the efficiency of electricity. The darker gray is additional efficiency improvements due to end-use energy efficiency benefit. And then finally we get to the 100% line. That's what we need to satisfy with wind, water, solar. So if I were to summarize, converting the US to 100% wind, water, solar would reduce power demand on average by about 36%, eliminate 63,000 air pollution deaths per year, costing over $500 billion, or 3.2% of the GDP, eliminate $3.3 trillion per year in global climate costs, create 4.5 million 40-year construction jobs, 2.2 million operation jobs, cost about 4 million jobs, require less than 0.5% of US land area for footprint and 1.7% for spacing. The cost of the whole system with storage and transmission with 100% reliability is between 11 and 12 cents per kilowatt hour direct cost. But there are barriers to this, including upfront costs, transmission needs, and of course lobbying and politics. And the upfront cost, just to give you an idea of what the whole system, the levelized cost of energy is the 11 to 12 cents per kilowatt hour. That's what you're really paying for everything. But the upfront cost, if you just want to say, well, let's buy everything today at the store, at Walmart, it would cost $16 trillion. I mean, that's the upfront cost. On a worldwide scale, it would be about $100 trillion. You think, well, that sounds like a lot, but actually each year the fossil fuel industry spends between $6 and $7 trillion. So payback time is on the order of 50 years of that, use that funding. But in fact, this would spread out over time, and you really look at the key thing is because wind, water, solar has high capital costs but zero fuel costs. You have operation and maintenance costs over time you have to account for, which is here. But to compare different energy technologies, you need to look at the levelized cost of energy, and that's what this number of 11 to 12 cents per kilowatt hour is. So then finally, so we've been developing these energy plans, and the goal though is to educate the public about them and policymakers and to engage businesses. And to that end, we started this group called the Solutions Project. And this really involves combining engaging business, involving culture, and science, and combining them to try to really provide information and hopefully educate people about this. And so there's a website, thesolutionsproject.org, that you can go and click on it. One page down, there's a map. You can click on the map, and up comes a plan for a state. Although I should caution that those are the older numbers, and we're going to update those in the next week or two with the stuff that what I showed you today. This group it's not a grassroots group, but it does do a lot of media outreach and tries to tell stories and to do videos and to engage the public in different ways and businesses. So there's this cartoon that came out. I'm not going to show you that because it's really probably geared towards like 16-year-old boys. But I will show you this. I will show you this, which is pretty. I think it's a video that's very inspiring. That was done by a lot of people come to our group and want to do things. And this Jason Silva is a videographer who came and said, "Look, I want to create a video for you guys," and I think it's a fantastic job. But we've had other people who have volunteered their time and efforts. But I'll show you this really quickly. Hopefully this will come out.
So here at Shots of Awe, we trade in the currency of optimism. We're tired of doom and gloom, fatalistic thinking the world is going to hell and all that. We need solutions to address the real challenges of humanity. See, I believe in boundless possibility. Human beings are a curious species because we have the ability to conceive of delightful, exotic, future scenarios. And we can actually move the popular will. We can pull the present forward and meet and actualize any of those possibilities. That's what we do. We pull the present forward into the future that we create, that we map out. Today, we hear a lot in the media about the energy crisis. We hear a lot about sustainability. We hear a lot about stranglehold of the planet. These are all legitimate concerns. But again, doom and gloom has been fatigued. We need solutions. So let's talk about the Solutions Project. The Solutions Project is an amazing new initiative led by Hollywood celebrities, brilliant civil engineers, the popular will of some of the smartest men and women in the world who have come together to leverage their brains to create a plan to take us 100% renewable here in America, literally 50 plants for 50 states by 2050 using technology that already exists today. The proposal is straightforward. Eliminate combustion as a source of energy. The sun gives us in one single hour more energy than we would need to power the Earth for a year. And the technology used to capture that energy is getting exponentially faster all the time. The fact that less than 2% of the United States land mass will support all of the wind, solar, and hydroelectric power generation required to meet energy demand is amazing. Now again, it all comes down to the fact that we need to think cognitively lean. We need to realize that this is already possible now, today, with existing technology. You change minds, you change paradigms. So again, I encourage all of you guys to check out thesolutionsproject.org, get educated, get involved, join the conversation. Thank you very much.
Thank you all very much.
Time for questions?
What about solar panels? Solar panels are made out of silver. There's a limited amount of silver enough. Is there any material to use, or how do you deal with that?
Well, we did do an analysis of the materials required for each of the technologies on a worldwide scale. We found that there wasn't a limitation because, especially with regard to photovoltaics, there are so many different choices of materials and types of photovoltaics that if one goes short, there's always another, and you can start doing recycling. But we didn't find a limitation. Other people have found limitations with solar. Although, some types of technologies there could be more limits than others. There's so many different.
I wonder how long it would take cities and states and things like that to update their municipal laws and things to allow solar in certain places that will cover somebody's view, or the sound of, we've had situations here with the wind turbines that might, were suggested for over near Riga. So those are the little, things that are sort of harder to deal with, and then people having to buy new equipment.
Yeah, that's definitely goes into the lobbying.
Could you repeat the question?
I'll repeat it. Yeah, she's saying it's at the community scale, especially, there are obstacles, maybe not in my backyard obstacles, or concerns about certain technologies and their impacts. And that is always going to be an issue. And that's one of the things, like even the transmission issue, I think that's even a bigger issue because nobody wants to put transmission lines near them. So we're going to try to use existing transmission to the greatest extent possible, beef those up. But that's, you're going to need rights of way for that. But, wind is going up actually at a very fast pace, despite some places where it's having trouble because of concerns and these concerns, I don't want to argue about that. I can give you an opinion about different concerns, but it actually is going up very easily in a lot of places, but there are some places where it's not going up. So that's, there are communities that are going to try to oppose because they don't want anything. But the key is, the question is, do you want that technology versus something else? It's not, nobody wants to add anything to the environment. But the real question is, would you rather have like a coal-fired power plant in your backyard, or a wind farm, or a gas farm, or a nuclear plant? So it's really that choice that people have to make. And I think when you look at all the factors, like the air pollution, health reduction problems, I mean, burning things causes health problems to everything. And so I think that's the biggest thing to consider. I mean, all the complaints about birds, noise, flicker, things like that, a lot of other people don't see that. The prices of wind, and there have been several studies now looking at the price of houses near wind farms, and there is virtually no change statistically over the United States and even over parts of Europe. But you do see near gas mining, coal mining, property values do decline, but not near wind farms. So if you actually look at the meta studies of this, it's going to be an issue. I don't want to deny it.
What do you see as the biggest obstacle to full implementation by 2050?
It's really, if everybody wanted to do this, it could be done. So it's not a technical or economic limitation, it's social and political. I think there are many people aren't convinced that this is a good thing, or they're stereotypes, or they're being fed that information by some people in some cases. So I think it's a social and political issue, not technical or economic. Because, if we all got together and everybody wanted to do it, it could be done. Like in a huge Manhattan-type project way. Things are changing. And last year, 54% of all the new electricity in the U.S. was wind and solar. But we needed a 99.9%.
Can we repeat the question? I think that's...
Sure. Okay. Yeah, wait a minute.
What recommendations do you have for us actually creating or adopting a national grid that would actually transmit these alternative energy sources?
Well, ideally you'd have the transmission system organized in advance, the location of all the wind farms and solar farms planned in advance. You can make things more efficient, especially with wind and solar. You don't want, if you geographically disperse wind, for example, you can make it more efficient because when the wind's not blowing in one place, it can be blowing somewhere else. So all the sites can be planned in advance. The transmission lines can be planned in advance, but that has to be done at a national or at least regional level. So I don't think there's a lot individuals can do about the large scale, except to vote for people who support doing that. But individuals can do a lot on their own towards this end, including maybe next time you get new appliance, get an energy efficient appliance. Electric cars, very efficient. Solar on your roof. Weatherizing your home. Sometimes changing habits in terms of commutes. There are a lot of things individuals can do, not only to reduce their energy use, but to use more efficient energy, and then if you're interested in engaging policymakers, tell them what you want. And engage policymakers and join a group that engages policymakers. Yeah.
Well, I know that with those plants that shoot the lights off the mirrors, that birds will fly through the beams and get instantly incinerated. But how about with the underwater turbines? Will they affect sea life, for example, whales and like dolphins and stuff like that, the bigger ones?
That certainly has been a concern, but I mean, these things rotate so slowly, and you can put meshes in front of them to, if they were, because they're not like, first of all, with the underwater turbines, people have considered how to reduce impacts on sea life. I mean, whales would be, they're not going to get hurt because these things are rotating so slowly. I'm sure a whale would stop and move. But they are thinking of putting filters, like meshes, to prevent big fish from going through. With the sea, the number of birds that are killed, you have to put it all in perspective. I mean, it usually comes with regard to wind. So the Bird Conservancy and the Fish and Wildlife Service estimate about 440,000 bird deaths per year in the U.S. from wind turbines. But they also estimate that communication towers kill between 5 and 50 million per year. Cats are about 80 million per year. And buildings are 1 billion per year. And then if you look at actual studies, but the real thing is, how does wind compare to other energy sources? And compared to coal and natural gas, wind is actually 1/10 the bird kills per kilowatt hour because of the mining, the destruction of habitats due to mining in the case of mountaintop removal by coal and destruction of local habitat by gas mining, transport, the air pollution from coal and gas, kills people but also animals, and also the buildings. So 1/10 the bird kills. So when you put up a wind turbine, you're replacing conventional fuel, and that's reducing bird kills, even though you do have a finite number of bird kills. Same with CSP. I mean, the number of birds incinerated is true compared to all these other sources of bird deaths, but it gets headlines in the news because it looks pretty weird. Yeah, we have a bird.
About bird, so I don't know if you addressed this, but water consumption. How do you? Is there any indication of that in the study?
Yeah, we studied actual water impacts of all these. So all thermal power plants, like coal, gas, nuclear, and biofuel, they all use water for cooling. And wind, biofuel power, but wind does not use any water at all, except for the manufacture of the turbine, which is a tiny amount. Solar PV, washing the panels, requires some water, but like there's one plant I went to in Arizona, and they don't ever wash the panels, they just let the rain wash it. So because it takes, if they don't pay somebody to wash the panels, they save money. And they calculated that the loss of efficiency was less than the cost of having to pay somebody, plus the water savings. So they don't need to wash the panels. Concentrated solar panel power, that requires water for cooling if you use water cooling, but there's actually another option of dry air cooling that they would use in deserts that you lose about 5% efficiency, but you need no water for cooling. Geothermal, with binary plants where you recycle the water, there's nothing because there's no water lost, it's just one water going down and up. Tidal wave, offshore wind, you're not using any water. And the only other one's hydroelectric, which you get evaporation off the surface of the reservoir. But the reservoir surface has multiple purposes, including recreation and water supply. So it's not all attributable to hydroelectric power. So there's really, compared, if you use biofuels like ethanol, you would require 10% of the entire U.S. water supply to power the U.S. vehicle fleet with ethanol. Based on the irrigation rate of corn in the United States is about 13%. If you extend that average irrigation rate to the additional ethanol you need to run the vehicle fleet, that's 10% of the whole U.S. water supply goes to corn ethanol. So the same, cellulosic is about half of that. Yeah, go ahead.
Yes, if you looked at the, how to get to 100% solution, like carbon tax, cap and trade, feed-in tariff, maybe that sort of.
Yeah, well, there are a lot of mechanisms to get there, and we identify some of them, like the ones you just listed. We don't propose any specific one. I think it's more up to the local or state or federal governments to decide what the best mechanism. So we're trying to develop these plans and roadmaps, and then let the local legislatures or state decide the best mechanisms to get there, because there are many ways to do this in terms of legislation. So we don't have one particular one way to do it.
I'm with this group that wants to ban horizontal fracking in Michigan, and so we're here trying to get volunteers to help circulate petitions to get it on the ballot next year. You talked about fracking and air pollution, fracking natural gas and how it causes air pollution. Could you talk a little more about what it does to the water and the amount of water needed?
Okay, well, fracking, you need water laced with chemicals, sprayed with under high pressure to crack rock. So it uses a lot of water. I think last year it used 70 million gallons in California for fracking, although that's not for shale, especially oil fracking in California, so it's not probably even more for shale rock. But in terms of the chemicals stay in the groundwater, but the rock cracks, and so you get extra leaks. Well, first of all, you need a cement casing for when you frack a well, then you put a cement casing into the well, and 5% of all cement wells leak immediately, and 50% leak over the life of the well. And 5% is immediate. These are industry numbers. These are not just made up. And so you do get this leak, and even after you capped the well, there's still leaks that go on. And so there's a lot of methane, especially, that leaks into groundwater. And that methane can get into residential areas and into agricultural areas, into farmlands, and cattle, sheep. I really recommend the movies Gasland and Gasland 2 by Josh Fox. They really show, just from a perspective of somebody going around with a camera talking to individuals, normal, everyday people living rural lives, agrarian lives, just everyday citizens talking about their experiences with gas coming out either of their sinks, hurting their farm animals, their dogs, their children, and people having to leave their homes as a result of this fracking. So it's a really incredible set of films. I'm sure a few of you have seen. I think that's all I'll say about that.
Yeah, so the word baseload is a loaded word. And how do you fit that word into your analysis?
We think baseload is obsolete in our future world, because baseload is a flat supply of energy, essentially. And right now, you have a flat supply, but flat supply, the load looks like this. This is the demand for energy is flat, is not flat, it's like this, very irregular. And so right now, we use either hydroelectric or natural gas, mostly, for providing peaking power to meet those peaks. So the baseload is only getting you up to somewhere below where all those variations occur. And especially if you have higher penetrations of renewable, which are variable and intermittent, then baseload actually becomes more expensive to maintain. Because you'll have a lot of times where you just don't need the extra baseload because you have too much energy. And the baseload, you didn't need that baseload. And so the new paradigm is really kind of trying to match the power demand with mostly the combination of these renewables plus storage plus demand response, trying to shift the times of peak demand. And using hydrogen, when you have extra wind and solar, it's actually okay in the system because you can then use it to produce hydrogen, you can dump it in, let's say you have extra electricity, you can actually then heat the soil with that extra electricity. And then use that heated soil later for heating homes. So in our system, like the results I showed, there was the only baseload was, I think, geothermal was used as baseload. Even geothermal, you can use that for heating sometimes. Yeah,
Your Michigan model had 0 for geothermal. And yet a lot of efficiency can be gained by the loops. And we envision, that being a significant part of savings. And yet even out to 2050, we had 0. Now, is that because you're interpreting it really as heat, or what do you?
Well, yeah, there's
different use for ground source.
Could you repeat the question?
Yeah, the question is, we have 0 geothermal, and why is that, basically? And first of all, that's for electricity, but not for ground source heat pumps. Ground source heat pumps would be, there's plenty of energy for ground source heat pumps. So, but there are only 13 states in the US that have really good geothermal resources. And when I say really good, reasonable expected costs in the next 20 to 40 years. And so it's not to say that in Michigan, we couldn't have deep geothermal with the boreholes. It's just that based on current resource analyses, there really isn't anything there. Or not a lot there. It doesn't mean it can't be done or it can't be found. It's means people haven't looked hard enough. But for other types of geothermal, like heat pumps for heating your home, I would definitely, in fact, I would recommend strongly, next time you need to heat your home or to heat water, you get a heat pump that's a ground source heat pump that takes heat out of the ground. It's actually more efficient than an air source heat pump because the air temperature fluctuates so much, but the ground temperature is very stable. Yeah.
I've heard, or an argument I've heard against solar power is the recyclability of a retired solar panel. Are they toxic once they're no longer used, and do they end up in a landfill?
Well, I can't answer that. The question was, are solar panels toxic when they're no longer used, and do they end up in a landfill? And I can't see why all the components can't be recycled. Maybe in current practices they're not recycled, although I don't know that many that are being thrown away. But I like in the automobiles, like all the car companies that are making electric cars, they're going through great pains to recycle all the components of the batteries. So I imagine that's the same for the solar panel. I can't speak with authority on that, what's going to happen. I can say that in the worst case, you're still getting the benefit of air pollution reduction and climate reduction, and you want to reduce the ground contamination in landfills as much as possible. But like mining, it's a one-time thing versus if you have them for 30 years, you're saving 30 years worth of pollution. And so if there's a one-time cost, it's a lot less net damage to the environment than 30 years ago. But having said that, I totally hope that recycling is done for all of those pieces. Yeah.
Thanks for your talk. Can you say a little bit about some of the challenges about portability and transmission? Especially with wind, portability and transmission. If the model is in Michigan to go far more toward wind,
okay.
How do you get that energy from where it's windy to where it's not windy?
Yeah, so in terms of wind, so the question is the affordability of wind and its transmission. Well, the cost of long distance transmission, first I'll start there. If you have a 2,000 kilometer line, the mean cost, and this is because you can amortize the parts, different parts last different lifetimes, but some of the longer lifetimes are up to 70, 80 years, and some of the other ones are like 30, 40, 50 years. The amortized transmission cost is, the mean is 1 cent per kilowatt hour over 2,000 kilometers. And the range is 0.3 to 3 cents per kilowatt hour. So if your average electricity bill is 13 cents per kilowatt hour, and the worst you'd have to pay is 1 cent per kilowatt hour to transmit 2,000 kilometers, from the Great Plains, that's not too bad. So right now there's a dilemma, in the East Coast, should they develop the offshore wind, which is more expensive than onshore wind, but have short transmission, or should we take Great Plains wind and transmit it to the East Coast? This Great Plains wind is 3.7 cents per kilowatt hour, unsubsidized, and 2 cents subsidized. Transmission is only 1 cent per kilowatt hour. Even for 2 cents, it's still in the order of 5, 6 cents. Right now, it's cheaper to do that than it is to use offshore wind for short transmission. So those are choices you can make. Would you rather have local wind in Michigan? You have a lot of wind resources. It's not developed. So I would imagine you could develop the low-hanging fruit first at low cost, pretty low cost, rather than transmit. But you could also transmit. Maybe the back.
Does anaerobic digestion fit into your mix?
Well, we're trying to avoid anything related to combustion, but anaerobic digestion to produce, what is?
More for methane to hydrogen?
Yeah, so in terms of methane, the one thing that if you use methane in a fuel cell, and you obtain the methane from like a landfill where it would otherwise leak naturally to the atmosphere, then that would probably be the best way to use methane, as opposed to getting methane and burning it. So methane in a fuel cell is pretty efficient in terms of, you still have carbon dioxide coming off, but there's pretty much no other chemicals. Because when you burn things, you create all sorts of other chemicals. So that's really the only kind of, what I'd say, biofuel that there are probably other similar analogies, but methane from a landfill to a fuel cell, hydrogen to produce, or to use directly in a fuel cell, that could be an application, but we don't do calculations for that. Yeah.
Okay, maybe one or max 2 more questions.
With the depth of research that you've done, and the analysis, and the breadth of it, and the urgency of the situation, and knowing that the social political are the possible impediments, and the urgency of this relative to time, as an Adrian Dominican sister in many groups such as ours, we would wonder how your voice and your information could get magnified so as to have a genuine substantive effect.
Give me an audience with Well, I should say, we've had some reasonable success in getting information out. We did meet with the Vice President of the United States, and he was actually very excited about this and supportive. We've met with governor staff in New York and California, and actually several other states expressed interest. Actually, in California, we met with Governor Brown's staff in October and proposed, we'd written a paper specifically for California to go 100% by 2050 and 80% by 2030. And then in January, in the State of the State address, he actually adopted 60% of our plan.
Wow.
He's going 50% by 2030. So that was a step. And also in New York, we also had success. The governor's office asked us for 5 suggested first steps. We provided them, and he adopted 3 of them. So there is some movement. It's not a lot, but it's going that direction. But anything you can do to help, I'm supportive. One more.
This would be sort of a twist on what was just asked, and that is, since most of your solutions seem to be large scale in terms of looking at the United States as a whole or looking at states as a whole, when you're in a situation where the larger scale is not necessarily attainable because of the political or social impediments, are there any solutions that might be attained through a smaller scale, i.e. through a smaller community such as Adrian, taking some steps along this path?
Yeah, well, I definitely think that each community can do a lot to try to go towards 100%. In fact, our local community, Palo Alto, claims that they have gone to 100% renewable energy. I don't know if I believe it, but they do claim it. So there's a lot you can do. I mean, because cars are coming from all sorts of places through Adrian, you're not going to be able to control transportation, but you can encourage through vehicle charging. I don't know, does anybody here have electric cars? Yep. Great. No, we're actually good. So, but it is growing. I mean, there are now there are 700,000 electric cars, I think, in the world, almost getting up to 1 million. And, but it's trying to solarize the city, trying to maybe have government cars electrified, try to give incentives for clean energy, solar, and if you could put up the wind farms nearby here, that would be awesome. I think each community can do a lot. They might not be able to go technically 100% because you can't produce all the wind and solar and all the energy in the city itself. But you can do power purchase agreements. In fact, our university, it actually just reduced 80% of its carbon emissions, like last week, because it shut down the natural gas plant. It was right actually outside my office, ironically. Literally, it's right outside my office. They shut it down, and they're replacing the energy with 3 things: heat exchanging, and they're using wind and geothermal power purchase agreements from off campus, and they're putting up a huge amount of solar on campus. And heat exchanging such as like they're taking, when computers eject heat, that could be used in some other part of campus. At the same time that cold air produced in some parts of campus can be shifted around. So they actually have this huge heat exchanging system that prevents them from having to use a lot of energy. And also more efficient heating and cooling as well. They have the ice storage I mentioned before, but they've actually replaced 80% of their carbon emissions. So each community can actually go through all their uses of energy and try to replace things one at a time through all sorts of these innovative technologies that are existing right now.
Thank you very much, Mark. This was really enlightening. So we see really it is possible to go this way. You don't have to just blindly believe what the fossil fuel industry tells us, and especially what's going on in the next future in Flannery County with all the pipelines that are in plans. We really have good arguments that they have no right to take land away from people, from public domain and so on. There's really no need to do this anymore. Before we retreat to a small reception in the lobby, I want to just make a few announcements. Mark will also be around tomorrow morning for a meet and greet in the University Center in the living room from 8 to 9. And also later at the day at 1:30, I think we said, right? In the Weber Center?
Yes.
1:30. And that's open to the public again, right? If somebody wants to ask some more questions.
Where? At Weber Center.
In the Weber Center, which is just over there. And I also want to announce, as I have you as an audience here, that we scheduled the second speaker, or actually it's the third altogether in this William Issa Endowment series, and that will be David Orr from Oberlin College, who is a really very known educator as well as advisor to the president of Oberlin College, and the college went really very far in terms of sustainability. And it's really great to have him here. And that will be November 11th. We have that speaks scheduled. And now please join us for dessert in the lobby. Thank you very much.